We're going to review the ratio test. Here's your background information, example 1. Okay. Although I think you can determine if this series is convergent or divergent from the nth term test. Just kind of put a thought there to it for just a minute. If you were to find the limit of the nth term and you were to use L'Hopital's rule in the numerator, your derivative is always going to be 3 to the n times ln3. Then differentiate it again, you're going to get another one of the same with an additional factor of ln3. Okay, your numerator's just remaining basically the same with an additional constant multiplier. But the derivative of the denominator, okay, is going to eventually go down to a constant. So the limit of the nth term would give us an infinity, which is not 0, which tells us that this series diverges. However, this particular example is in the ratio note card, so we can also determine that it's divergent from the ratio test. So we need to review that test, so we're going to apply that test here as opposed to the nth term test for divergence. But just wanted to point out, if you did see that I didn't have to use the ratio test, well, don't. It's a little more work than the nth term test. All right, so the ratio test has us find the limit as n goes to infinity of the ratio of 2 consecutive terms. And to do that setup to get 2 consecutive terms, okay, every n we see we replace with n plus 1 to get the term that follows a sub n. So as a reminder, we just replaced n with n plus 1. And divided by the a sub n term, but we know that's going to be multiplied by the reciprocal. I think we did a little cleanup, anything that we can simplify. Okay, I think we see that 3 to the n will cancel with 3 to the n, leaving 3 on top. The n squared here won't cancel with this. We're just going to have to bring that through. Okay. You could pull the 3 out front if you wanted to. However, you can leave it in right here. As n goes to infinity, we're going to get indeterminate. So you could either use L'Hopital rule, or you could think, well, if I were to expand this denominator, the highest exponent would be a 2. The leading term would be n squared. And an n squared over an n squared for n behavior, as n goes to infinity, would have us compare the coefficients, okay, of those two terms. So I'd have 3 over 1. So this limit's going to go to 3, which is greater than 1 in the ratio test, which tells us that this series diverges. All right, will this series converge or diverge? Maybe the ratio test can tell us that information. All right, I can simplify this yet further with the factorials. All right, n factorial over n plus 1 factorial. So it's like saying 5 factorial over 6 factorial. Okay, well, I can expand this, create a few terms. Let me do that. Okay, this is where I might lose some students sometimes, although I think we're past that. But just to remind you, n plus 1 factorial means it's n plus 1 times n minus 1, etc. And I can just slap on a factorial here. So to expand this, we can pull out a n plus 1 factor. So when you think about n factorial here and then n plus 1 factorial down here, okay, what it reduces down to is just the n plus 1. The n factorial is going to cancel with every term after this term, okay, like you can see up here. All right, plug in infinity. So you're going to get 0. Let's see, it's going to be 0. And according to the ratio test, because this value is 0, it's a value less than 1, this series is going to converge. All right, so the ratio test was used if we have a combination of factorials, exponents, etc. But it was really used for determining intervals of convergence. So that's where we're going to go next in this video. Is we're going to go to note card number 19, radius and interval of convergence, and review a couple of those problems there and how this test helped us determine the interval of convergence. So note card 19. Okay, of course we have our background up above here. Let's look at example 1. I am actually just going to find the radius of convergence for this series. For the other three, I'm going to find the radius and interval of convergence. Okay. So just the radius for number 1. All right, so if we're asked to find that, we know it involves the ratio test. Okay, so it's the limit as n goes to infinity. So see, this is a power function because of a base of x. Okay, so if we were to differentiate or integrate, then it would be with respect to x. Okay, so there is a distinction between x and n, but for us to find the radius of convergence, we're going to find the limit as n goes to infinity. Okay, this setup gets kind of involved. So hopefully nothing will disappear. Okay, we're going to involve the -1, but we know that the absolute value, gives us a situation to where we can ignore them. But it's good in the setup to show it. Okay, let's see if we can do some cleanup. Okay, the negatives will go away. Let's see, when I divide out a quantity x minus 2 to the n, I'm left with only one of them on top. So my numerator will be x minus 2. Okay, that took care of all that. Over here, it looks like I can cancel a 2 to the n with a 2 to the n down here, leaving a 2 in the denominator, but I still have the n up here with the n plus 1 down here. Okay, and so what we did next is we pulled out the absolute value of x minus 2, since the limit is in terms of n, as n goes to infinity. We just kind of uncluttered it so that we could focus really on finding this limit with respect to n. So n over 2 times n plus 1. And I could have pulled the 2 out front as well, or excuse me, I could have pulled the 1/2 out front as well. All right, so absolute value of x minus 2, and we'll kind of study this right here. Okay, that limit is going to be 1/2. So this is what we end up with. 1/2 times the absolute value of x minus 2. Okay, well, if we're trying to find the radius of convergence, thinking about the ratio test, if I want this to converge, I need to have this less than 1. Because otherwise, if this is going to be greater than 1, it's going to diverge. Okay, so the radius is not 1. Again, we need to isolate the absolute value. So this is the same thing as saying absolute value of x minus 2 is less than, multiply both sides by 2, is 2. So my radius of convergence is 2. Okay, so if I was going to talk about the interval of convergence with regard to this, the center is 2. We can see the center is 2, so I'd go 2 to the left and 2 to the right. So before I did any tests on the endpoints, okay, my interval of convergence would start out being from 0 to 4. And whether I needed to include the 0 or 4 would be determined by using tests, series tests, by letting x be 0 or x be 4 and x be 4 and doing the tests on those. But those are going to be kind of involved, kind of complicated, and we only have a limited amount of time, so this is not the one I want to test the endpoints on. Okay, so this is all we were looking for. Okay, example 2. All right, so example 2 is given to us in expanded form, and then we do have an expression for the nth term. So we're going to go ahead and set up the ratio test with that nth term. I'm not going to rewrite it here. It's on your paper. Okay, noticing the structure of that nth term, I'm going to pull the x to the n up to the denominator and I'm going to put it in front. And I'm going to increase the exponent to n plus 1. So in parentheses, I'll have n plus 1, but in n plus 1, I'm going to replace n with n plus 1, so that makes that n plus 2. And in the denominator, I have 3, but the exponent needs to be increased. Replacing n with n plus 1 also gives n plus 2. Multiply by the reciprocal of the nth term. Okay, and because x of n was on top, I'm going to put it in the denominator here, multiplying by n plus 1. Oh, I think that was a 1. All right, doing a little cleanup. X to the n cancels, leaving an x on top. The n plus 2 is not going to cancel with anything, so I'm going to just write it here. 3 to the n is going to cancel. I'll have 3 to the first over 3 squared, so 3 to the first will divide out with one of them down here, so I have a 3 in the denominator. Okay, now I'm going to work on this, and then I'm still going to have n plus 1 because that won't cancel with anything. Alright, so that's equal to, I'm going to pull out the absolute value of x. I don't need to put the 3 in absolute value because it's already positive, so I'm pulling this out of the problem, focusing my attention on this limit right here. Okay, well that limit's going to be 1. All of this is 1. So this is equal to the absolute value of x over 3. If I want it to converge, I'm going to make it be less than 1. Multiplying both sides by 3, absolute value of x has got to be less than 3. Radius of convergence is 3. The interval of convergence before I test the endpoints, well, the center is 0, so I have to stay within 3 units of 0, both to the left and to the right. So prior to any tests on the endpoints, okay, my interval of convergence is going to be -3 to 3. Okay, time to test the endpoints. I'll start with -3. So going back to the nth term of the series, replacing in x with -3. Alright, again, I'm going to put that up front. So I'm going to have -3 to the n. I think I got it all there. Right. Okay. Probably want to take a little bit of time and expand this. What I mean is inside here you can multiply -1 times 3 and raise both those factors to the n power. So again, this is -1 times 3, so you can make that -1 to the n times 3 to the n. Okay, and we want to do that for the denominator here. Okay, times quantity n plus 1 over 3n times 3 to the first. Okay, and if we think about cleaning this up, I can cancel these two. Okay, it is alternating. Okay, but we can see that if you take the limit of the nth term, that's going to infinity. So actually, this is going to diverge. So we won't include the left endpoint of -3. Moving on, I know I'm going kind of quick. X equals 3. Okay, so look at the structure here. If I test x equals 3, it's just going to be a +3 here, so it's not going to be an alternating series. So I end up with this kind of same situation. And I'm just going to put ... thinking about the time here, knowing you see what's going on, that this is also going to diverge. So our interval of convergence is just going to be -3 to 3, not including the endpoints. So both of these series, when replaced with -3 and 3, diverged by the nth term test. Okay, let's take a look at example 3. I think 3 and 4 go kind of quick. They're not as involved. Okay. So let me get the setup of the ratio test. A little bit of cleanup. Leaves an X on top. We'll pull up the absolute value of X and left to evaluate the limit as n goes to infinity of n over n plus 1, which this is going to be 1, so we get absolute value of X. We want it to converge. We make it less than 1. Our radius of convergence is 1. And our interval of convergence is going to be -1 to 1. So I'm just going to put I of C. Okay, we need to test the endpoints to see if we need to include either one with a bracket. So let's test x equals -1. Okay, going back to the original series. Okay, if x is 1, we get 1 to the n, which is just 1 over n. That's a divergent. Am I testing -1? Hang on. Whoa, hang on. I'm testing x equals -1. Hold on. So that should be -1 to the n. So sorry. Whole different ball game here. Now it's an alternating series, and we're going to do the Ast test. It does pass 1, and it does pass part 2. So actually, this is a convergent series by the Ast. So converges Ast. So I'm going to come back up here and put a bracket on -1. So -1 when replaced in for x would make that series converge. Okay, I must have been doing a test on x equals +1. Whew. Okay, so if x is +1, right, we have 1 to the n, which is just 1 over n. This is divergent, so we wouldn't include the right endpoint, so we're good to go. Divergent p-series. Okay. All right, moving quickly on to example 4, just to get another practice problem in. Let's see what happens there. Okay, so let's do the setup of the ratio test. Okay, let's do some cleanup. We're going to have x on top times n factorial times quantity n plus 1 factorial. We can yet do some more cleanup. We saw this in a previous problem when this situation came up. Okay, so I'm still going to have x on top, but I'm going to have n plus 1 on the bottom. I'm going to pull out the absolute value of x. The limit as n goes to infinity of 1 over n plus 1. Okay, evaluating this limit is going to give us 0. So I'm going to end up with that absolute value of x times 0, which that product is 0. Okay. And let's see, 0 is less than 1 already. And since 0 is less than 1 by the ratio test, this is going to converge for all x. Okay, so our radius of convergence then is going to be in infinity, which tells us that our interval of convergence is going to be -infinity to infinity. Okay, and I wanted to get to this last example because it did provide a unique situation, a different one that doesn't come up all too often, but there was one more case that didn't show up here, and that's where you use the ratio test and you get a value greater than 1 and it diverges. And what that tells us is if this is greater than 1, that the series only converges at its center. That was the third case.